Okay, so I want to look at the last problem on our review activity. This problem considers motion by both diffusion and settling. So it says calculate the average time it takes a glucose molecule to move 1 centimeter by diffusion in water. And then the second part is to calculate how far a 10 nanometer particle of standard density travels in that same amount of time, but by gravitational settling. So let's start with the first part of the problem and calculate the time that it takes a glucose molecule to move 1 centimeter by diffusion in water. So in class, we derived this expression for the root mean square displacement in one dimension, which was 2 times the diffusion coefficient times time to the 1/2. And so if that displacement in one dimension is a centimeter, and we have this diffusion coefficient of glucose in water that equals 6.7 times 10 to the minus 10 meters squared per second, then we can solve for t. And if we do that, then we get a time that's quite large, 74,000 seconds, which is about 1 day, 20.7 hours. So that's a pretty long time scale to move 1 centimeter. So then how far does a 10 nanometer particle, so a diameter of 10 nanometers, travel by settling in that time? So we're going to have to calculate a terminal settling velocity, right, and multiply it by this time that we've just gotten in order to get a displacement x due to gravitational settling. So we can start by assuming that we're in the Stokes regime. And that means then that our terminal settling velocity is this expression that's been coming up time and again. Now in this case, because we are considering such a small particle, right, 10 nanometers, then it's going to be crucial that we calculate this Cunningham correction factor. We can go ahead and assume that we're looking at something spherical. We have no dynamic shape factor, but we will need to use the more sophisticated version of the Cunningham correction factor since we're looking at dp less than 0.1 microns. And since we're looking at this 10 nanometer particle in air, and air at standard conditions, then we can use that mean free path of air at standard conditions that equals 0.066 microns. So be careful of our units, right? If we use this mean free path in microns, then we're going to need to use our diameter of our particle also in microns. 10 nanometers, right, is 10 times 10 to the minus 3 microns. And now if we plug all of those values into this complicated expression for our Cunningham correction factor, then we get a value that's large, about 22.98. Right, this just indicates that for these very small particles that have diameters on the order of nanometers less than a micron or 0.1 micron, then this Cunningham correction factor is becoming very large, very much non-negligible. So we're going to use that then along with the standard density and the diameter of the particle to calculate our terminal settling velocity. Here we've used 10 to the minus 9, right? It has a diameter of 10 nanometers. And again, we're looking at air at standard conditions, so we use this viscosity. And if we plug all those values in, we get a very small terminal settling velocity, of 6.91 times 10 to the minus 10 meters per second. Very small. So the last step then to calculate the displacement due to this settling is just to multiply that velocity by the time scale that we calculated up above, that 20.7 hours. And when we do that, we still get a displacement that's fairly small. 5.15 times 10 to the minus 5 meters, or about 51.5 microns. Right, so the big takeaway from this problem is that for the very small particles, like this 10 nanometer guy, the more influential mode of transport will be Brownian motion. So I don't travel so far by settling, I travel further by Brownian motion when I'm small.